Hello everyone, today I will be talking about three things. I will start by explaining acid and base, then I'll be moving to pHs, and my last topic will be the indicators. I also will have in my video a download link for the slides of this topic, prepared slides, not the slides I'm writing now in. And let's start. So now let's start with acid and base. We all know by now it's like acid is example for an acid something like HCl, and for base something like NaOH. And we know that HCl is an acid because it has this ability to lose this proton, and the base has the ability to lose this hydroxyl group. So for acid and base, there is three ways of looking at acid and base. First one, according to Arrhenius point of view. The second is Bronsted, acid and base, and the third one is Lewis theory for acid and base. First, for Arrhenius. In Arrhenius' definition for acid, it says that the theory says that the acid is actually the substance that has ability to produce hydronium ion, or what we call H3O plus. So this is the acid in the acid has the ability to produce this hydronium ion, or the acid is a substance that has ability to produce proton in general. For base, in case of Arrhenius, it is the substance that has ability to produce hydroxyl ion. Example for that, like we said before, HCl, which has ability to give off proton, and the base is NaOH, which can give off hydroxyl group, the OH. The second way of expressing acid and base is according to Bronsted concept. The Bronsted concept says assumes that the acid is the proton donor, which is H plus, and for the base is the proton acceptor. So in that case, it's like the acid will lose in the reaction H plus, and the base will accept in the reaction an H plus. So not like if we see here, like in Arrhenius, we said that the acid gains the proton, and here loses hydroxyl. In here, Bronsted is actually losing proton or gaining proton. The third way of looking at acid and base is according to Lewis theory. In that case, we will be looking at acid as the substance that has ability to accept electrons in general, and the base will have the ability to lose electrons. So in that case, we could see in Lewis theory, it's a general theory that it can be applied on substances that do not exist in a solution, because you will have, like in case of biochemistry, sometimes you don't have solution like water or any solution, so it will be just a reaction between acceptor and a donor. Acceptor for an electrons and a donor for electrons. If I look back again, and for something like acid and base, something like HNO2, if I reacted this acid, which is it's an acid, if I I reacted this acid with water, we could see that the water will act here as a base. So first thing we have to know about water. Water can act as an acid and it act as a base. In case of an acid, like we said, in case of an acid, it has, in, in case of a base, it has this ability to accept a proton. So you will have in that case H3O. And in case if it acted as an acid, H2O would just give up one of its protons, so it will be OH minus plus H plus, which will give it to another substance. So you could see that here it accepted a proton, so it acted as a base, and in that case it acted as an acid. For HNO2, if it reacted with water, because HNO2 is actually an acid, the water in that case will just act as a base, because its pK is actually higher in case of acid, so this is why it will act as a base. So the H2O will just accept, because it's an base, it will accept one of the protons of the HNO2. By that, the water will be H3O plus, and for HNO2, it will lose the proton, so it will be NO2 minus. You could look, if this is a plus, by that, this base is actually converted into a conjugate acid. And if you looked at this part, you could see that because it started as an acid, but now it has this negative charge, which means it converted into conjugate base. So it's actually doing the opposite thing, because it's in case of an acid, it just lost an electron, so it became a base. And for this one, because it accepted a proton, it converted into an acid. If I go back again and look at one of the pronisted acid and bases example, and in that case I would look now at water like the example before, but this time the water will act as an acid. So to be able to use water acting as an acid, this means I have to have a stronger base, which is NH3. The ammonia have this NH3 have 3 protons, and the nitrogen have 2 lone pairs. In that case, because actually water is less basic than the hydronium, so the hydronium will act as an base, the ammonia will act as an base, and the H2O will act as an acid. So for H2O will give off one of its protons, and it will become OH, and this proton is going to go to the NH3, and by that NH3 will become NH4, so it will have 4 protons, and for that the nitrogen will be carrying a positive charge. So you could see that the nitrogen have given off its lone pairs to the water, and the water became conjugate. The opposite of acid is conjugate base, and in that case this will be conjugate acid, because it became now it has one extra proton that it can give off if in case of reacting. If I looked at something like weak base, something like carboxylic acid. The carboxylic acid, which is H3, C double bond O OH is actually a weak base. Why it is a weak base? Because in case of if it is like so, it is second example. We will be looking at acetic acid. So acetic acid has the ability to act as a base or act as an acid according to the other substances that exist in the solution. Something like if acetic acid in presence of sulfuric acid, H2SO4, we know that H2SO4 is a strong acid. This strong acid has the ability to give off one of its proton and forming HSO4 minus, and this proton will be enforced in this oxygen, and you will have the C double bond O will be C double bond O H, and from that side it will be an OH, and from here the side is untouched. So you could see that you have here you started with two lone pair on the oxygen, and in here you have only two lone pair with a positive charge. So you started with a weak base, but you ended with a strong conjugate acid. And in case of sulfuric acid, you actually started with a strong acid, and this strong acid actually because it lost one of its proton will act further as a weak base. Now if we instead of use the other way for acetic acid to react, if it acts in presence of something of a strong base. This strong base have a lot of OHs that will be given off inside the solution. So what will happen to the acetic acid? In that case, the acetic acid will actually act as a strong acid, and the base, which is a strong base, will be giving because it's a strong base, now it's accepting one proton of the acetic acid, so it will take out this extra proton from the acetic acid. So the acetic acid will be like that way. You still have the two lone pair on the oxygen, and although you started like with oxygen OH, you ended up with oxygen with a negative charge and two lone pair. On the other hand, the base will take that H and it will form HOH, and it will be a weak acid. You could see that I always flip. If it starts like a base, it will end up a conjugate acid, and if this it started as strong acid, so it will be conjugate base. Okay. Now if we look at the pKa, actually the pKa of acetic acid is equal 4.76, and for something like H2SO4 is actually equal minus 5.2. So this is what defines if acetic acid is gonna act as a base or act as an acid. So if you have pKa with a substance that reacting with acetic acid below the pKa of acetic acid, which is 4.7, in that case it is in sulfuric acid pKa is actually minus 5.2 because it's a strong acid. So This means the acetic acid will act as a base, will be forced to act as the opposite component, which is a base. But if you have like pKa, which is higher than 4.7, because if you have a base, this means you will have pKa higher than at least 15. This means you will end up by being you will enforce acetic acid to act as a base. Now, because we are like covering this part as sort of biochemistry, we will be looking at acids and base of amines and alcohols. You know, in case of amines, you have the amine group, which is NH2, and in case of alcohols, you have the OH group. So in case of amine, if you started like with amine like CH3 NH2, now if you because its pKa is equal 40, this means it is a very weak acid. So if I reacted this very weak acid with something weak base, but still have a higher pKa than the pKa of this weak acid, the amine actually will kind of lose one of the hydrogens, so it will form CH3, NH with a negative charge plus, of course, the base will accept this oxygen, is this proton forming HOH. In case I reacted my amine NH2 plus something which is a stronger acid, it's pKa like H sulfuric acid. Like we said before, its pKa is actually minus 5.2. In that case, the amine will accept the extra proton from the proton donor, which is the strong acid. So we will have NH3 positive charge plus HSO4 minus. This is what happens to amine in case of present with a weak base, and in case if it present with a strong acid. So if it reacted with a strong acid, it will actually act as a base and and if it reacted with a strong a weak base or a base, it will act as an acid. For alcohols, one example for that is methyl alcohol C2H5OH. C2H5OH is known to be a weak acid with a pKa that is around 15.9. So if I have ethyl alcohol in presence of a weak base that will just have OH minus, this means my alcohol will give off one of its protons and end up with a negative charge over it. So you will have C2H5O minus, and you started with 2 lone pairs, you will end up also with 2 lone pairs. Sorry, you started with just 1 lone pairs, you end up with 2 lone pairs. In case here, if we reacted C2H5OH, I will have it with a strong acid like we have done here H2SO4, which is sulfuric acid, because the pKa of this acid is higher than the alcohol. The alcohol in that case will act as a base, but a strong base, and it will accept another proton from the sulfuric acid. So you have C2H5O H from this side, and you have also H from this side with and the ketones. So you know that esters will have, if I have dimethyl ether, something like that, it will have this oxygen with two lone pairs, C2H5 plus HCl. So I'm comparing now ether, not comparing, but I'm just looking at ethers in presence of acid. It will be acting as a base, of course, because it's a strong acid. So it kind of force the ether to act as a base. And if I have something like ketones, so ketones, if I have something like acetone, it has the C double bond O, which is the ketonic bond or carbonyl bond, CH3. Plus BCl3 if I acted this one with boron trichloride. So boron, first let's look at the first case. In the first case I have the ether. So the ether have this oxygen that have two lone pair that can accept a proton. So you will have C2H5O, so it will lose one of its lone pair, and you have this proton C2H5, and the Cl will be just negatively charged. And for in case of ketone with the presence of boron trichloride, in here you could see that because this is like a ketonic group, the C double bond O with its four lone pair, it's 1, 2, 3, 4, two lone pair, so it will the carbonyl group is the one which will accept the proton. So you have C double bond O, and in case of the extra proton that coming from BCl3, it will come to the carbonyl group, not like we have seen before to the oxygen group. So you have here the one who accepted the proton was the oxygen. In case of here, you will just add this extra proton to the carbonyl group. So you will have BCl3 minus, and here the carbon of the carbonyl group will have positive charge over it, and you have the oxygen with two lone pair. We will compare the electronegativity of oxygen, nitrogen, and carbon. You could see that any compound that will contain carbon will be a weak acid, while any compounds that will start to that has nitrogen will be more stronger, and in case of oxygen will be the strongest. Why is that? It is because of the electronegativity. So the electronegativity defines the strength of the acid. The more electronegative the atom, the more acidity the compound will be. This means if I have like OH, if I have oxygen, it will act more acidic than the nitrogen. It will act more acidic than the carbon. If I this means if I have something like C2H4 and CH3 NH2 methylamine, and something like CH3OH. What is the strongest acid in those? We could see that the strongest acid will be the one which have atom that has the higher electronegativity. So methyl alcohol uh, will be more acidic than methylamine, and this in turn will be more acidic than the ethane. So if I just like organize those according to the acidity, I could say that the highest is the CH3OH and the lowest is the C2H4. So now we will be talking about the pH and the pKa. First, the pH. What is the pH? The pH is the negative logarithm. So the pH is actually equal to the negative logarithm to the base 10 of H3O, the hydronium ion. We can also replace the H3O, like I said before, by the H plus. So pH will be equal minus logarithm to the base H plus. We could say that the pH is actually the negative logarithm of the concentration of protons in the solution. And we have three cases of the pH. We have the pH below first equal 7. We will call it, if my negative logarithm to the base 10 is equal to 7, this solution will be neutral. And if it is lower than 7, it will be acidic solution. And if it is higher than 7, we will consider the substance to be basic. If you look at the reaction between a strong acid and a strong base, something like NaOH, it will give me the OH will accept the proton of the Cl, and the sodium and the chlorine will be left out as sodium ions and the chlorine, negative chlorine ion, and the H and OH will be combining, forming H2O. So I will have salt and water, and this salt in case of solution, it will be dissociated, and the complete dissociation because it started with a strong acid and a strong base. Now if I looked at something like weak acid and weak base, in case of weak acid, if I used something like CH3COOH plus something like NH3, the acid in that case, which is a weak acid, would lose the proton to the NH3. You will have CH3COO minus plus NH4. If I wanted to know what is the pKa, what is the Ka value of this compound, you will have to the reactant divided by the concentration of the reactant by the concentration of the product. So the product here, the concentration of the product over the reactant. So in the first, in the second case, if I have something like that case, it will be CH, the concentration of acetic ion multiplied by NH4 divided by NH3 multiplied by CH3COOH. For a reaction with something like, so Ka should be equal product divided by reactant, but we are not looking at the product itself, we are looking at the concentration of the product divided by the concentration of the reactant. We will divide the pKa into values. If the pKa is lower than 1, we will consider the solutions that have this value to be acidic, strong acid. And if it is have something between 1 to 5, it will be moderately acidic. But from something from between 5 and 15, it will be weak acid. And above 15 will be extremely weak acid. Okay? Buffer solution. So what is buffer? A buffer is a solution that contains weak acid and its conjugate base or weak base and its conjugate acid. So the buffer usually the use of the buffer because the buffer has the ability to maintain a relatively pH constant even when you add the acid or base. So it has this like it stabilizes the pH or keeps the pH at a certain values. So what is the rule of why the buffer is important? You have one buffer in our body that is very important. Something like CO2. So you have CO2 that is out from metabolic reactions. If if it reacts with water, it gives off. Actually, this is there is an equilibrium in this equation. The water in that case will just act as would react with the CO2 forming H2CO3. The H2CO3 will act as a weak acid. This weak acid will be will react further with something basic, something like water. In that case, if it is further reacting with water, it will react with water given of one of its proton to the water to form hydronium ion, and HCO3 will be out. The HCO3 in that case can further accept any proton from any component in the blood to form again a weak acid. So it's like a reversible reaction that maintains the pH in our body with a constant value. Moving now to what we call the acid-base titration. So the acid-base titration is actually a reaction between an acid and a base in order to know the concentration of one of them. So I will use a known concentration of one of them. If I know the concentration of the base, I will use this knowledge to figure out what is the concentration of the acid. In doing that, we do it in the lab, and we use a micropipette that we have a pipette that contains what we call the known concentration of titrant. So the titrant is a substance that we know its concentration already, so it have known concentration. and we will add it to a beaker that contains the analyte. And we will know the concentration of this analyte by knowing how much titrant we use. In order to use that, we use what we called as indicators. So inside our flask here, we add something else called indicator. This indicator is actually a substance that have ability to change its color according to the pH. So it will switch the color by switching when the pH is switched. So if I have something like, if I'm adding here a base, that I'm adding it to unknown concentration of an acid. If I need to know what is the concentration of acid and I added an indicator, each drop of here, a certain drop of here that will make this acid convert to a base, the ending point of my reaction will just switch the color of this indicator from a certain color to another. So in the next video, I will be moving to show some examples on how to calculate the pHs of a solution.